All right, let's take a look at another example. This will just be what we would call an inelastic collision or a hit and bounce. So we have a 0.25 kilogram red car moving rightward with a speed of 60 centimeters per second when it collides with a 0.5 kilogram blue car moving leftward with a speed of 30 centimeters per second. After the collision, the red car is moving leftward with a speed of 40 centimeters. What is the speed and direction of the blue car after the collision? That's what we're asked to solve for. Again, I will draw a picture of the before and after collision scenarios to visualize what's happening. All right, I've gone ahead and drawn my before and after collision scenarios, and in this case, we don't know the direction or the velocity of the blue car after the collision. So we're looking for essentially the sign and the magnitude of the velocity of the blue car. I'm going to begin by once again completing my momentum table here with the quantities that I know already. I know that before the collision happens, the red car has a mass of 0.25 or 1/4, 1/4 essentially, and a speed of 60. And in this case, rightward is going to be positive, so I'm going to make a note of that. I'm going to say that this is the positive direction, okay? It's important to define your directions before you start a problem like this. So that would mean that my momentum of the red car before the collision is a positive 0.25 times 60. That's going to be basically 1/4 of 60, 15 kilogram centimeters per second here. All right, now my blue car has a mass of 0.5 and is moving leftward. That's going to be a negative velocity, so a negative momentum, with a speed of 30 centimeters per second. So 0.5 times 30, or half of 30, is going to be a negative 15 kilogram times centimeter per second. So I know that the system together, right, the positive 15 and the negative 15 will give me a total momentum of 0, right? They will essentially cancel out. So to get the system, once again, we just add red plus blue. That's how we get this one, all right? Now, after the collision, I do know enough information to solve for the momentum of the red car. I know that it's going to be leftward here is negative again. So in negative 40, really it's going to be negative 40 here, times 0.25, so that's going to be negative 10 for the momentum. I don't know the blue car, so I'm going to leave that as an unknown. I can go ahead and say that the momentum will be the mass of the blue car times the final velocity of the blue car. I don't know what that is though. But I do know that for momentum to be conserved, they should equal 0 when I add them together, because before the system's momentum was 0. So after, it should still be 0. Again, the change should always be 0 for systems where there are no external force, which is what we'll be dealing with in this class. Now, you could start to solve this using an equation, or you could just take a look at this momentum change column right here. So we're going to take a look at this column today in this example. If I think about it, from the before to the after collision, the red car had 15 units of momentum, and now it has negative 10, right? So that would be a change of what? Negative 25 kilogram centimeter per second. Essentially, right, the red car lost 25 units of momentum. Where did it go? Right? Well, I know that momentum is conserved, so that if the red car lost 25, then the blue car should have gained that 25. It should have gone to the blue car. All right? So that means that the momentum of the blue car after the collision should be 25 units more than it was before. So I know that basically what I'm saying here is I'm going to add that 25 to the initial momentum of the blue car. So that would be, what would that be? That would be negative 15 plus 25. That would mean that the blue car after, right, so the momentum of the blue car after the collision is going to be equal to 10 kilogram times centimeter per second, right? And I know that again because the red car lost 25 units of momentum. In other words, the change was a decrease of 25 from the before to after. So the blue car must have gained all that, must have gained 25. So it's going to go up from negative 15 up 25 to positive 10, okay? That means that the mass of the blue car times the final velocity of the blue car is that's the momentum. That's going to be 10. And so if I know the mass, the final velocity of the blue car is just going to be that 10 divided by, again, the mass in this case is 0.50. And you'll see here, if I show my units, that the kilograms will cancel. And that will give me 10 divided by 0.5 or 1/2 is just 20 centimeters per second. And in this case, it's positive. So I know the blue car is going to be moving to the right with a speed of positive 20 centimeters per second. All right, not too bad, right? So using the table is a huge help. Let me show you another way that you could have solved this same problem using the table. If you were just instead to look at the after collision column, like we did earlier, you know that the momentums of the red and blue cars together must equal the system's momentum. So I could have just said -10, right? So the momentum of the red car plus the momentum of the blue car would be equal to 0. In other words, the momentum of the blue car is going to be equal to 10. And I would have gotten the same exact thing, right? It's just two different ways of thinking about this problem. You can think about it like the loss of one is the gain of another, or you can think about it like together they must equal the same system momentum as before. But again, using the table is a huge help when solving problems involving collisions. Let's take a look at another example.